which part of the world you are in. Uh, so let's first introduce our webinar series and its objectives. So critical transitions in complex system seminar series is being jointly hosted by IIT Madras and Potsdam Institute for Climate Impact Research in Germany. This webinar series brings together experts from fields such as climate science, combustion, neuroscience, fluid mechanics, ecology, etc. So every field included, and aims to disseminate the state of the art in the prediction of critical transitions in these diverse fields of study. The webinar takes place every month on the last Monday of the month, with some exceptions if there are some emergencies. Before I introduce the speaker, a few housekeeping notes. I request everyone to turn off their microphones and please use the Q&A box in Zoom to ask the speaker your questions. We have kept ample time at the end to discuss doubts and clarifications. With that, let me introduce today's speaker. Professor Sudeshna Sinha is a professor at the Indian Institute of Science Education and Research, ISER, Mohali. She had previously served as Dean Faculty Affairs and subsequently Deputy Director. She has authored over 100 research papers and holds several patents, with her work featured in Nature News and Views, Scientific American, The Economist, and MIT Technology Review. She is a recipient of the Birla Award for Physics and the prestigious J.C. Bose National Fellowship, and is a fellow of the Indian Academy of Sciences and the Indian National Science Academy and the World Academy of Sciences. She also serves on the editorial boards of leading journals including Chaos, Communications in Nonlinear Science and Numerical Simulation, and Proceedings of the Royal Society A. Today she will speak about evolution beats random chance, or it's about performance-dependent network evolution for enhanced computational capacity. The floor is all yours.
Thank you, Sujit. So should I make it full screen now?
Yeah.
Okay, I'll try that.
Yeah, excellent.
Okay, right. Okay, so thank you very much for the generous introduction. So the first thing I should say before I start is that this is about reservoir computing, and it is not really my area of expertise. But it has sort of recently caught my fancy. And the reason I thought it was appropriate for this forum was because, stripped of, the engineering motivations, it is a very interesting complex system problem, really. So I do feel this whole field of machine learning, which has now occupied so much of our academic space and interest, I think it does bear looking at through the eyes of a complex system or a dynamical systems person. And so I thought I'll share some very recent results on this with you all. So, of course, as I said, most of my work is not here, and this is really just very new for me too. And in the unlikely event that you want to know what I actually do mostly, you can have a look at my web pages, and so I'll leave you with that. So let me get on to what I wanted to share with you today. So I will actually just talk to you about two very specific papers. Strictly speaking, it will be just this one paper, and I will take maybe 10 minutes of your time at the end to indicate the results of this, just to tell you the broadness of the first set of results. And I don't have mugshots of everybody really, but the person not in the picture, the one who's not me, is Manish. I thought at least the young people who have done the heavy lifting in this work, their photos should come up here. So that's Manish out there. And here, this is Anil. So these are the people who have done a lot of the heavy lifting in these papers. Okay. So there. So just to set the stage, so we are looking at artificial neural networks. And what is the whole big deal about them? The thing is that they are universal function approximators. So in principle, they can be utilized for wide-ranging tasks like forecasting dynamics maybe, and they have enormous scope in that sense, in principle. Now in practice, they of course offer this very powerful tool, but they might need impracticably many neurons to actually do the job with reasonable accuracy. So one of the reasons why this whole machine learning thing has blown up to the extent it has is because we have the technology now to throw at a very old formalism in some sense. So we are just throwing more and more machinery at it, and of course it is getting better naturally in some ways. Still, one of the drawbacks to my mind is that one does not a priori have an estimate of how big the network should be in order to be effective. So it's more or less trial and error. It's prior experiences of the researcher, not of the program. So it's what we say in the sidelines. What did you use? How big was your program? Stuff we exchange. In the side notes, not in the journal papers. But this is how we somehow fix the size. So it is really a priori. It is quite ad hoc, and we tackle it on a case-to-case basis. And maybe sometimes through some random search in a very large hyperparameter space, which of course, necessarily can only be very sparsely explored. So from an applied perspective, of course, it would be of value if you could think of some framework in which you can judge or gauge how big is big enough, or when are you sort of given some limited resources, what is the best way you can use it? So how big do you have to get? And but for me, somehow it is more really a more basic question. Basic could be thought of as more fundamental in some ways. It is of interest to uncover what concepts can you use which will lead you to the smallest effective networks. So will lead us or guide us to that class of networks which are the smallest but are still doing the job. How can we get there? Because in the space of networks, it is like sitting in a really small corner. You can't just throw a brute force search at it and hope to get there. So there has to be some other idea, if one can think of it. And in uncovering that idea, if we could give a somewhat broader principle, hopefully adaptive, so that you can start small, start with a small seed and synthesize a good network. So this would also allow us later to be prescriptive, because it can give you a recipe. Because if you have somehow found a way to reach this sweet spot in these networks, which are giving you enhanced capacity, this could be your prescription to guide you to getting it. And from a broader perspective, is there some unifying underlying feature that pops out when you stare at these special networks that come out of what we are going to do? And so in the even broader perspective, if you want to think of the quest, you could frame it in this, kind of endeavor to understand structure and function. So in some sense, you want to do something, the function, and what structure suits you best and how does it get there is what we would like to get. And in some sense, I would think that in the engineering point of view, it is very function-based. In more theoretical and more, maybe in the basic sciences point of view, it's more structure. So we should sort of find a bridge to get from function to structure and from structure to function, of course. And so this is what I will try and share with you today, is some idea of a performance-dependent network evolution. And I hope to tell you how this got us to some optimal specific network structures, which efficiently solved a bunch of tasks. Okay. And what we would leverage is reservoir computing principles, because it suits dynamical systems people the most. It's a way of really understanding the network as a complex system, and at the same time, of course, keeping the ideas of functionality which you need from the engineering and applied point of view. Okay, so this is the idea. So I'll put the central findings up front and hopefully provide demos, demonstrations, or support of these findings as I go along. Okay, so that would be the idea. So what did we find? And then this is hopefully to, it's like a trailer. So hopefully everyone will stay put to find out if it really did find these things. So let me, give you the trailer first. So what we found was that evolved networks, I haven't told you what the evolution strategy is. That would be, of course, what I will do very soon. But these evolved networks, they outperformed random networks, without a doubt, clearly. The second thing was bigger was not always better. In fact, the evolved networks were sometimes ridiculously small compared to the random networks, while achieving the same performance. So it was delivering the same goods, but with much less resources in some ways. And what were the basic properties which seemed to pop out? One was sparsity, unexpected sparsity in some sense, unexpected from the what is expected from, say, a random network point of view. And they seem to adhere to scaling laws in this number of nodes and density space, which indicated a certain relationship which seemed to hold across these evolved networks. They also had a distinctive asymmetry in the input and readout nodes. So this was the second important thing which came out. And so we hope that this could, give some understanding of process-specific network evolution. And, later on, if we understand what you got, we could work backwards and say, okay, this is a prescription. This can be used for synthesizing or designing optimized complex information processing mechanisms. So that's the hope. So as Sujit said, this is a general audience. So I will start at the beginning, at least for a little bit. I will have to say the beginning is also a beginning for me because I'm kind of, getting my hands warm in this field, just about. But I will say upfront, it is actually, when you think of it, a very, very simple framework. So this all falls under reservoir computing, whatever I'll tell you now, except there is a tweak and a twist to the tail, which I will tell you. So what is the reservoir computing? What is the basic principle? Input signals are mapped onto a higher dimensional reservoir from which there is a readout, which gives you the output. So it has three layers. Of course, the first is the input layer. The world gives you an input. That's what you have to deal with. This is blue stuff here. Is the dynamic input. It's hitting your reservoir. This whole bunch here is your reservoir, which technically falls under the class of a recurrent neural network. Okay, much like a echo state network or a liquid state machine. So from this, the output is tapped. These are the red guys here, and there's an output layer. So there are three layers: input and output, obviously, and the processing layer, which is high dimensional, onto which it's projected and then it projected back, is the reservoir, the green guys. So if I had to write an equation for it, the equation would be simple. Dynamic input signal is, say, U of t. It is fed into the reservoir. And then what we do, how is the output got from it? It's a very simple readout mechanism. So in fact, the reservoir is left to do its own stuff. And the output is obtained from linear regression with one-step training. I'll say this one more time. So let me first write down the equation. So this is the dynamics of the reservoir. At time t plus 1, given from the time t. So one part looks like this, just itself with a leakage term. Then there is a part which gives you the weights and the input. And then there is this readout layer, which gives you the desired output. Okay, so all the output is obtained from this mapping out here. Okay, it's a simple readout mechanism and to obtain the desired output. So what are these objects here? This object is an adjacency matrix, just the way we understand adjacency matrices, and they represent connections, just as any adjacency matrix does. So there are n reservoir nodes. How they are connected with each other is all that information is sitting right in here. Okay. This one specifies the inputs. So some nodes of the reservoir receive this time varying input, react to it, of course, and this is captured in this term out here. This object is an output weight matrix, okay? And this one is the only one you're going to train, okay? The reservoir is just sits there. So this one you're going to train. And how is it trained? It is trained to minimize the difference between the output of the reservoir computing box and the ground truth, the real actual gold standard of the output, the actual output. So this difference is going to drive the training of this matrix out here. And we typically use linear regression. So it's a one-step training. You know, it could be a Moore pseudo-inverse, but we have used ridge regression. But some regression method would do the trick. So essentially, all the training is there in just one spot. So which makes it a bit cheap in terms of training. So each node dynamics is, of course, determined by the previous state. Okay, t plus 1 is determined by t and the external stimulus and a nonlinear activation function. So the reservoir matrix is, contains all the information of the reservoir states, stimulated by the external signal, and then goes on to the next state. So the parameter alpha, which was there somewhere here, stuck in here, this one, okay, is often called the reservoir information leakage. It determines the amount of the past reservoir information, which is leaked over time. And the real-time output, which I always will denote with a little twiddle on top, this cap out here. And it is going to be obtained as a linear combination of the reservoir states, which is given by the equation above. And the key feature, I repeat, is that only the readout is trained, whereas the network remains fixed. So which is why it appeals so much to dynamical systems people, because you can stick in your favorite dynamical system there and watch what happens. So for instance, maybe this is your dynamic input, some stream fed into your reservoir input layer here. This is your guy doing its own dynamics. Here is the output layer, which needs to be trained. Okay, the W in here, W reservoir here, W out here, and this should match this, and that is how your readout layer is trained. And in the response inside, of course, there'll be many patterns, and all the patterns should add up together or have a linear combination, which should be this one. That is the basic idea. So what have we proposed? So what we propose is idea, which is to say that let us start small. Don't sort of use this maximally huge kind of thing. You know, usually you have a big machine, you make it like 1,000 nodes or something. You know, let's not start big. Let's see if you start small, how can we grow the network to an optimal size, which is just enough, you know, to do the job. Okay, so you grow it, you morph it, you adapt it, and you get to the right size. Okay, not too much. You don't have to overshoot it. And our surprise was you could really do with very small networks. I'll show you in a minute. So how do we grow it? The key idea then is to generate a minimal network. And what we would also try to do is that in this evolutionary growth that we will see, we will have two things. One could be, you know, in fact, we started off with that idea. We said, just grow, you know, keep adding more and more and more and more. And of course, at some point, it will be the right size and it will do the job. And of course, that is a strategy. But then I'll show you in a minute that that's not the best strategy. That will still get you to a bigger than needed thing. Why is that? Because as you add nodes, also remember that some nodes might become obsolete. Some nodes might, you know, not be, useful anymore in the scheme of things. So the parsimonious structure which we would like to get at would also need to shed weight. You know, it's much like, for instance, like a an organization which has to pink slip its, guys who are not pulling their weight. So in this set, we have to pink slip some of these nodes also. So node addition, and we want to bring in node deletion. Okay. So to achieve a evolution like growth, we would like to continuously add and delete nodes from the pre-existing network and see where it leads us. Of course, we'll have to have a feedback loop, because one strategy is to just add and delete randomly. I'll tell you how far that gets you. Short answer, not very far. So what we would like to do is to add and delete with some performance dependent feedback. Okay, so that we intelligently or somewhat carefully do this addition and deletion. Okay, so add and delete, how do we do it? So the primary function of module which adds is to, of course, add new nodes to whatever you have. So you start very small. So we start with 2 nodes. So obviously 2 nodes is almost never enough for any task. So it has to grow at least somewhat. So you start adding new nodes to the pre-existing network. And you keep checking its performance and seeing, where it's going. So what is the performance dependent part? The new node can be added. Of course, it gives you connections. Each connection has a in and out link with some probability. It can be input receiving node, or it can be a readout node with some probability. Usually we just take it to be half, with probability half, it's an input receiving or a readout node. And what do we check? We check the performance with this one to do that particular task. And the network is updated only if the performance of the new network is better than the previous one. So if it doesn't get better, there's no point going bigger. That is the whole point, okay, of the addition. So it is performance dependent. You don't just keep throwing and making it bigger and bigger and bigger and hope for the best. That is not what you're doing. The module D, which is the deletion, also works in tandem with A. So it keeps continuously removing the unnecessary nodes. So it's like a pruning mechanism, which is, in case you became bigger than you really need when you added in the last step, you take a sort of performance audit and say, okay, are these nodes pulling their weight, or can we chuck them? So a randomly selected node will be removed if the performance of the network without it is better or exactly the same. So by that I mean, be careful, better or exactly. So if it's exactly the same, it still goes out, because which means I could have done with a smaller network. I could have done without it the same task. So it will only not be deleted. You will only not be thrown out if you actually better the performance. Otherwise, we will throw you out because we like smaller networks. So A and D orchestrate the whole network evolution by retaining only those nodes that improve overall performance and eliminating nodes that don't assist. Okay, so old network, for instance, something comes in, you assess it, and then maybe something goes out and you keep growing. So this is the basic framework of the performance dependent node addition and removal. So in a nutshell, modules A and D work together and hopefully get to an optimal level of size so that the overall performance is still there while sort of doing the job with the smallest possible network. And we only can do it because we have grown it. If you had started big and pruned it, actually you will get into all kinds of random local minimas and will not be able to do such a good job. In fact, the other way around, often you have order of magnitude larger networks. When you grow it, you really guide it to that special set of network that is doing the job for you. So here is a schematic of the node thing. I have been calling this N3. In a minute, I'll tell you what N1, N2, and all those are. But it's in the paper, so I'm sticking to that thing. This was the third idea we had. Clearly, we had 2 which didn't work, and I'll tell you that in a minute. So here it is, the addition and the deletion. And here you keep adding. If it improves, here you delete if it doesn't. And it keeps evolving till the whole thing does the job to a certain prescribed accuracy. So that you say, I mean, it has to be good enough to this extent. And if it is good enough to that extent, you stop the process and say, this is good enough for me. This network works. And then, of course, you inspect the network. How big is it? What are its features? And that's the next step. Okay. So we start specific 2-node network. That's my initial. I started, and then I keep adding it, and I keep checking if I come down to this desired performance. That is, the error is lower than something which I have prescribed. That is what the world wants. And when that is achieved, I stop. Okay. So here is a 2-thing: input layer, output layer, reservoir. This object is what I have shown before on its side, of course. Now this grows up to this, and I keep this feedback loop here in order to continue growing it till I reach an error which is lower than the prescribed one. Just another way of schematically saying, I have explained each of the modules separately, of course. Just another picture to tell you one important thing. Now, how big a network needs to be depends on the complexity of a task. In some sense, it's almost obvious. The size is almost a proxy to the complexity of the task. So I will tell you in a minute what each of these tasks are. We have tried 7 tasks, actually. These are all benchmark tasks. And for instance, this one is a mapping task, a classic one-to-one mapping task from sine, cosine functions and functions of these functions, etc. And this is also a pretty standard task of chaotic trajectory generation task. And we've also done others which are what are called NARMA tasks, which are nonlinear autoregressive moving average tasks. So these are discrete time temporal tasks which involve the mth order lag. So it represents past inputs. So that's a memory. It's a check for temporal information capability, which involves past input. So it involves memory. Okay. So this is memory free. This is, of course, chaotic trajectory generation. And there is a bunch of NARMA tasks, which I will show you in a minute. So this one, being a bit simpler, grows up to here. Very soon, it comes down to the level of error which we want. So in fact, at 5 to 10 nodes, and we are done. 10 nodes. For people who do machine learning, they're throwing hundreds and thousands of nodes. So a 10 node, which gives you the same performance, was a big surprise for us. This one took a little more and came down to about 27 or so, but still enormously less than what you expect. Okay, I'll go and show this. So here is a picture which summarizes this a little bit. So these are the nodes, these are the iteration. As it goes along, it grows up to a point. These tasks are the ones which I said involve past inputs. They are sums over past inputs, and they are called NARMA tasks, also benchmark tasks of nonlinear autoregressive moving average, and really a good test of temporal information processing, which involves memory. And these are one-to-one, classic one-to-one mapping of complex functions of sines and coses. And of course, these are, this one was a limit cycle and this one was a chaotic attractor, just to mix things up. Each one of them grew to some extent. And this is the error, which plunged very quickly and sort of stabilized. So these are the number of nodes in the evolving network for different tasks. And this is the error for the different tasks. There are 7 of them, benchmark. Okay. This is a summary of the numbers, just the numbers. Okay. So for people who do machine learning, any respectable program you'll throw at least 100, And so look at the numbers that you need to get very good accuracy. So the sine cosine, which was just mapping sine to a cosine, the first simple one, was solved in 5 nodes, just 5 nodes. The slightly more complex task of mapping, say, a sine function to a complex polynomial of sines and coses, maybe third order, fourth order cos and sine functions, somewhat more complex. This was also solved pretty quickly in 11 nodes on an average. This is actually a hard task. This memory-dependent tasks of NARMA, they are hard. If you look at the benchmark around, they typically take fairly large networks to get reasonable accuracy for these tasks. So this was a difficult stress test for the program, but it managed. These are different orders. These orders tell you how far in the past you have to, your function, how many states in the past it's taking. This is 5, 10, and 15 is pretty way back. And so the average sizes keep increasing, of course, because the complexity of the task increases. And so, but the first one in 20, it was done, 55 and 75. Still really very low if you think of it. So the bottom line here is you actually need very little. You don't have to go so big. This was the first surprise to me, that how small you can be in order to do the job. And for the multidimensional phase space trajectory generation, Van der Pol oscillator, we achieved with 12 nodes, just 12 nodes, and Lorentz in 27 nodes. All of these are really, really small numbers. And these are the outputs in dashed lines, the true value, the ground truth in solid lines. And these are good, as you can see, matching of the actual output and the projected output. So it does a good job. Okay. If you want to do a better job, you can, of course, grow the thing a little more, because it stops when it reaches your prescribed error bar. If you want to do better, you'll just have to grow it a bit more. But the point is, within the accuracy which we asked of it, it did a splendid job. So the thing which we have found then is the existence, okay, of small networks with just a few nodes which can efficiently process the complex tasks, okay. And the other interesting observation is that starting from any 2 nodes, of course, it's a probabilistic process, right? You're throwing things and it's doing stuff, and there's some probability there. So it will evolve to slightly different sizes, okay, with slightly different structure, of course, also. And the different sizes will depend on the complexity level. But to carry out the same task, it is actually, we found that these sizes were clustered with very little deviation in size. So there seemed to be a characteristic small size which it needed for that task, okay. And in some sense, this is really on the other, very, very different from common practice. So I'm saying this again, which is you typically take a randomly connected large network, bigger the better. You have a big computer, what's stopping you? You take a huge, big, network to solve tasks, and maybe you're overdoing it. So this is the first lesson. There do exist small ones. So now the question, of course, I'll ask 2, 3 questions. One is, where are these small networks? Which ones are they? And before I ask it, it's probably, you may have the thought in your mind as well. But from this, one needs to ask 2 questions. Is it necessary for the network to be grown and contracted continuously? I mean, can I not just grow it? How bad? I mean, that sounds like the first thing you will do. In fact, it was the first thing we did also. Okay, so which is why N3 was growing and contracting, N2 was just growing, and N1 was uninformed growth. So we tried all of them, and I'll show it to you. And so also, if I just randomly grow it, I once in a while throw an extra node and make a bigger one. Is it not good enough? I mean, do I need a performance dependency at all? So these are the 2 questions. So we have to do a few control experiments to answer them. So we must challenge the performance-dependent network evolution with different growth strategies, if you want to have a reasonable answer to this. Okay, so let's try a couple of different growth strategies. So the first one is to see, do we need performance dependence at all? I mean, is it really necessary? I mean, maybe a little bit better, but how much better? Let's see. So we just start growing the network in an uninformed way. We call that N1. Obviously, it's the first thing we thought of. We think of it as a reference. So I just keep growing the network, and at some point it'll be good enough, and I stop. But there is no feedback to this model. Okay, it keeps going and it keeps going. Okay, it just by random chance, irrespective of task and performance, I add something, but it's growing. Okay, it is growing. Now the second thing is I want to understand growth plus contraction. Add and delete. Do we need to delete? It seemed as if I told you up front that I needed it, but let's see. So I think of another strategy which just grows with performance dependent feedback. So it grows only if it is good. So it's performance dependent, that it is, but it does not contract. Okay, so it can only expand the network. And of course, it expands contingent on its enhancement of performance, but it will not delete. So it's very kind organization. It keeps growing, no pink slips to anyone. Okay, so you can think of it as a partial network evolution because it only consists of the addition module. The D guy is not there. Now here is a picture which summarizes it. Okay, now this one is N1. So it just keeps growing. Okay, N1 is uninformed growth. Every now and then it'll keep adding, it'll keep growing. Okay, so it keeps growing. It's linear, just goes every time I add one. So it grows. This is N1, so that's N1. These are two different things for N2. So here I add, but I don't delete. You see, it sort of grows with this, but then becomes sublinear. Okay, this is linear, but this is, its growth stops, it saturates. So it also does better than uninformed growth. So if I put in performance dependence, it does do better. It definitely is an ingredient that's important. Okay, because this uninformed growth is way worse than this. Okay, because nodes are gone up to 500 here it hasn't. It's gone up to about 300 or 200. But N3, where I add and delete, so I'm always judging myself and seeing, am I enough, am I too much, all this. When I do that, it really saturates way down here. Okay, so that is the thing. Okay, so you do much better with addition and deletion, so expansion and contraction and a balance of that. And this is performance dependent expansion, and this is just straight off expansion. And here is actually a very busy plot, which has been hours and hours of computation have gone into this small set of boxes here. So I don't know if I can look at it too closely, but I'll just summarize it a bit. So these are all the 7 benchmark tasks. These are what happens to the nodes. These pink ones, I think we should have gone for a red or nice color, but anyway, we've gone for pink. Manish has gone for pink. So here it is. This is addition, deletion, performance dependent growth. This is performance dependent addition. And this is just uninformed. Okay, so it goes up. These are the smallest sizes that you can get for the tasks. These are for each of the tasks, different colors. This is a reference of a random network. So just Erdős, Rényi over the full range of sizes, just a random sampling of it, and you throw it at the task and see how well it does. Okay, so this is, as you can see, huge spread because just I've taken like a reference. Okay, now here this is uninformed growth. Its nodes are big. Here performance dependent, so it's somewhat less. And here addition, deletion, so much smaller. And look at the size kind of variation. When you prune it at the same time as you grow it, you really get a tight bound in the size at the end. Otherwise, you get this huge spread. Okay, here you actually go towards a more characteristic size. And right, I can skip this. This is more of the other tasks, okay? The same thing. Okay, and this is of the last two tasks, which is chaotic Lorentz trajectory generation and the van der Pol. Okay, so this was for the sine cosine. This was for the NARMA, one of the most difficult ones actually, and this is generation of chaos trajectories. So now a bunch of questions, more questions. So we seem to have answered that. Okay, this strategy of evolving, growing deletion seems to be the most efficient, gives the most parsimonious and the best results, and bigger is really not better. Okay. Now the question is, how are these evolved networks different from the commonly employed randomly connected networks? Erdős, Rényi say. Is there any scaling law which sort of unifies or underlies this network that you get, okay, when you're solving a task? Is there anything special about it? Because, it's such a small one, it's doing such a good job, like how, okay? Now here is a picture. Again, a lot of hours of Manish's time here. This is the density of the network, and which is number of links by the total number. So if you total number of links is m and size of network is n, Erdős Rényi will say m by n times n minus 1 is your density. And these are the number of nodes, and for different tasks. Now there are dots, the color of the dots, if it's near blue, it means it has very low error, okay? So the normalized mean square error is very low. So if you see dark colored colors, you mean you're doing very well. Those are the good networks. They have given you very good results. If you see this green and orange and red, they are not good because they're giving high errors. So the colors are the errors in here, okay? Now you can sort of see I've put circles all over. Those circles are actually just Erdős Rényi random networks. So I pick up a whole sample of random networks and I ask it to do the job, see what error it gives, and I give it a color, and it's it has a spot here. Now these dark colors, I don't know to the eye, I hope you can see it, seem to lie on a rectangular hyperbolic arc everywhere. Here. So when we looked at it, it looked as if the space, which is actually a 2D space of density and nodes, if I took random networks, it would fill the space. But the special points was on this 1D hyperbolic, rectangular hyperbola, which we have in this space. So it is really a very special line. In terms of measure, it's such a, random search wouldn't quite get you these points. The ones here, which are low nodes, are from N3. The ones which are bigger are N2, even bigger are N1. So there seems to be a scaling, okay? So if I put it on a log-log plot, that hyperbolic, rectangular hyperbola arm, I find a certain scaling of the number of nodes and the density. So there's a density, number of nodes scaling, which seems to be there across the growth strategies, okay? And so here is a particular picture that I have of many, all those tasks, 7 benchmark tasks, many realizations, and they seem to lie on these lines. Now, the way it is done is that, your node comes in, it has some chance of connecting with m edges to the existing thing. Now, this m has a min and a max. So if I take, if I take the mu, it would look as if the number of links is mu times n, mu being average degree. So if I then stick it into, our standard graph theory, it would tell me that the density roughly is average of the number of links that, that you make at every point you grow, divided by the size of the system. Now, since in this study, we had this number of links went from 1 to 5, so 1, 2, 3, 4, 5, the average of which is 3. you would think 3 by n, so the slope of 3, density is 3 by n, should be this blue line here, is what you would expect if it was just a random network. And indeed, if you just took n1, which is very close to a random network, uninformed growth, just keeps growing randomly, it is very close to 3 by n. It's about 2.86, but okay, not too bad. But the other things are significantly lower. Okay, they fall, they rise, the prefactor is much smaller. Okay, it's not 3 by n. So which means that the average degree is not the average links that you have put in. As you grow, your system is selecting out some degrees. So the average in degrees of the final network with respect to it is shown here. So you will find that if it was uninformed growth, it is very close to 3, as you would expect from Erdős Rényi or just standard random network theory. Otherwise, if it was with performance dependent addition, not deletion, it is lower. And if it is addition and deletion with performance dependence, it is even lower. Okay, this is across all tasks. And so in some sense, I would call this that you are actually going to a sparser, less dense network. Okay, so it's selecting out, because all of those were possibilities, because uninformed growth, it went like a standard random thing. But when you put in your performance dependent loop, addition and deletion, you sort of select out the sparser ones. So that is the selection which is somehow come into play. So one of the first features. Okay. We also looked at average clustering coefficient. I don't think this was very important. The referee asked us to do it and we did it, so I'm showing it. It's there. This wasn't so, to my mind, I mean, wasn't so prominent. All it does tell me is that this line here is for a random network. This average clustering coefficient and density. It's a standard graph theory relation. However, when you have the evolved networks by this N3, this thing, I will find the cluster of them below this. So in some sense, I am getting lower clustering coefficients than you would expect. So it is selecting out things with somewhat lower clustering coefficients. So it's less cliqued, it is spreading out a little more the information. It's not tightly bound in kind of cliques or triangles in some sense. However, I still feel that that may not be the most prominent difference. Okay. So, summary of this part: significant features of the networks evolved by different strategies is this: average degree is smallest when the network is evolved with strategy of performance dependent node addition and removal. Okay, these yield best performance, and I mean the ones which yield best performance are sparser compared to the ones with poorer performance. And if you look at it, that's the part which I find interesting, is that actually a random network has a huge spread. Okay, so some of them in that huge spread, there were also some small ones which were doing well. The point is to get to that small ones, and they were on that special arc which was given by that scaling dependence. Okay, so that is the whole part here. So in that sense, they emerge under this performance dependent thing. They are not only the lowest prefactor, but they also converge to low network size. Okay, and so in that arc that you got, the hyperbolic arc, the N3 actually occupies the lower end, okay, of that arm, because it is low. It also converged to low network size. Okay, right. Okay, this I don't need to show. So one last feature of this, and this is something else which we noticed without actually thinking too much, but it was this one was very, very stark and very obvious. So what was it? So what we found was that in the evolved networks, there was an asymmetric distribution of the input and readout nodes. So we started with this probability, half, as I said, half of it, 50% chance it can be input node, 50% chance it can be the readout output node. Okay, half chance. Fair enough. Now, if that is so, at the end, the number of nodes which are input or output should be about 50%. And now, if we talk about a common node, so a node which is input receiving as well as readout, both together, that I call a common node. This would be with chance half times half, so 1/4, so 25% chance of that, and 25% chance of it being neither input nor output node. So this would be what you would expect from a random Erdős-Rényi network, or N node. What we find is that N1, which is our uninformed growth network, also is like Erdős-Rényi, almost in every respect actually, and in this respect too. So, okay, its distribution of input, output, common and unique nodes are essentially like a random network. However, the evolved network had a significantly different kind of distribution. The input nodes were about 0.53, which is close to half, 50%. So that was more or less the same. But the mean fraction of output nodes overall task was 3/4, 75%. So almost a 50% jump there. Huge difference, not a small difference. And the common node also rises to about 40% from 25%, very significant. And the unique nodes fall to 10%. Okay, so really the distribution gets very different in the evolved nodes. It is obvious that it's favoring this readout. N2 also, that is the model, which is performance dependent addition without deletion, also gets higher output nodes, 58%. Okay, that's more than 50%, not as dramatic as 75%. And the common nodes also rises, not as dramatic as 40%, but to 29%. So it also getting there, but this one is really dramatic. So this is the bare data, very busy plot. So you might just, because there's so many tasks, so many colors, so many models, but the bottom line is just this, which I will summarize in words, that the important point here is that the evolution dependent network is shifting the readout nodes to this higher fraction. Okay, and in some sense you might think that maybe this is what it makes sense, because the linear regression, which is only for the readout layer, the training is all there in reservoir in that. So maybe by making that vector, enhancing that vector gives it more information processing capacity. But this we didn't put by hand, right? This is self-selected by the growth thing. So the growth has selected this out. Okay, though in hindsight it's a good strategy, but we didn't put in that strategy. The growth strategy itself gave this to us. Okay, and so this is a somewhat, if you want to go, so the other way of saying it is, I have limited resources. I can only grow up, have a network of this size. What is the network which works best for me? I can only be this size, but what should I choose to do the best job? And so this is another feature which you can put in there, which would help you maximize your performance. Okay. So this is the summary and outlook of this. At the end, maybe I'll take just 5 more minutes to indicate Anil's results. But let me summarize this part first, if that is okay with everyone. But let me first summarize this, and then I'll just take 5 more minutes for that, because I know it's getting to the hour. Yeah. Okay. So what have we done? We have proposed this concept of performance dependent network evolution, and tried to test it on different benchmark tasks, both ranging from NARMA tasks to complex functions to, of course, standard dynamical systems prediction tasks. And what we showed was that it did the job in a way which was much better than a comparative sized Erdős Rényi random network, a typical one. If I just pulled out one from the basket, it would do much worse than what a growth dependent one would do of the same size. And what it also showed by comparison of both performance dependence addition and without the deletion and with the deletion is that the deletion and addition outperforms every other growth strategy. So this adaptive expansion and contraction is what gives it the optimal size. Okay, and we also found the scaling sort of, that was very nice because we didn't know that it would come. It's in the space of the number of nodes and density. This is irrespective of performance, because you sort of put all the tasks lined up in that same picture, and we found that there was this relation which on which all these high performing networks seem to fall. Okay, so they exhibited some unique features, and one of them was this. Okay. We also found this asymmetric distribution of input and readout nodes, which also was really very clear, and these were not small numbers, just as it was not a subtle effect. It was really a big and clear effect. Okay. And later on, Manish found somebody told him that there are these, I don't know how much that is important, but I found it interesting. So I put in this comment here that for certain gene regulatory networks, in fact, across species apparently, there appears to be a higher fraction of readout nodes in these networks. So I don't know if it has any great meaning, but this higher fraction did come out of this particular strategy. Okay, right. So in some sense, you can think of it, of course, as a growth model, evolution model, which beats chance, because if I just took a random network, so if I, for instance, in an appendix in this particular paper, we have done the maneuver test, for instance, and found out the p-values of the evolved networks and a random network. And it is without doubt, I mean, the null hypothesis can be rejected, off the bat, because there's such small p-values, there is no way just random chance would have given you those networks. Okay, this is the absolutely kind of clear message from this. And if you thought of a brute force search, where you look through the architecture and you see where can I find this magic network, that would be a very onerous task. That would be it would probably you wouldn't find it, because the space in which it lives is essentially a 1D curve in a 2D space. Okay, so you can see from the measure theoretic point of view, it is not a good call to go looking for it in a brute force search. You would rather grow to that point and sit there. That is the bottom line. Okay, so it sort of narrows down the search space and gives you a prescriptive, like a recipe. So now maybe you can find a designer random network because you know the properties that you should look out for. Okay, so this is, I would say, like the last message for it. Okay, so now I have to ask maybe Sujit, if I can take 5 minutes to just indicate this result. This is not part of it. In case anyone wants to see this.
Yeah.
Okay, I'll take 5 more minutes. Yeah, promise, no more. I will wrap up. So since this is 5 minutes, it's just a statement of this result. Hopefully there I gave you some details. So let me just state this one. It's a little bit of a spin-off, so I thought I should state it. That was reservoir computing. Much of what I'd done, whatever little I'd done in machine learning, was in feed-forward neural networks. That was what I had been doing. And so I went back to my old friends and told them, let's sort of see if this works for feed-forward neural networks. That is what most people are putting out there from the engineering point of view. So can we grow an artificial neural network in the feed-forward neural network formalism through dynamic evolution? And so what Anil and, whom I'd mentored a bit during his PhD, so he thought of doing this through gradient descent. It was not technically an easy thing to do. And the reason for that is that there are some smoothness conditions and some continuity conditions which have to be satisfied. So he had to do network size dependence is a discrete jump. So there was a little bit of technical thing which had to be put in. His code is on GitHub. But what he did do was that he started small, and then he managed to add, subtract just like this during training and get to these very small networks which did the job, even for feed-forward neural networks. I just had to say two technical things. He had two methods actually. One is called auxiliary weight, which directly controls the network size. So it puts the network size as a parameter which is optimized in your backpropagation. And the second one uses what is called a controller generated mask, which modulates the neuron participation. So in some sense, the first one is cheap in the early stages because you're training such small networks, fataфат you do it. But the second one, actually, he could parallelize on a GPU very easily. So it lends itself to parallelizing the second one, controller generated mask. So it's just a technical point. So he did both of these, and both approaches optimize the network size through gradient descent. This is through gradient descent. So different from, in that sense, technically very different, though the idea in some sense is the same. Okay. And so one was structural modification, where you can modify the network structure through the parameters. So is there a neuron, or is it present or absent? And you can do it through activity modulation. So you have a fixed maximum size, but you can continuously control the contribution of each of the neurons. So basically, your effective network is a much smaller one in this space of maximum size. Okay. And so the single neuronal weight in the first one is like the network size. Okay, it can be optimized through gradient descent, along with weights and biases, the usual stuff. And the second one is the controller mask, which has fixed size, but masks through a learnable mask filter, controls neuron participation. Complementary ways to achieve the same thing. And this is literally my last slide. So what one could do was to train and evaluate these neural networks on various tasks. These were actually harder and somewhat different tasks. One was, of course, nonlinear regression, which we did with Bessel functions, just for the fun of it. A whole bunch of different Bessel functions, compose them, through lots of complicated things for it to figure out. And the second one was a classification task, which we haven't, is not so, reservoir computing is not very suited for it, but this one was. So this one was spirals. So we kind of looked at spiral data sets where the classification task is hard because you can't find a line to classify the, separate the patterns. So it's a classic benchmark problem. So it outperformed, it worked very well, outperformed corresponding static networks. So if you took a network of that size, did the work, it was way better than that. Okay, the grown one, because it grew to a special sort of configuration. Okay, so it grew to minimal, appropriate, or optimal sizes. And what we also found was if I took a massive one and started pruning it, what I would come to is actually a much larger one than growing bottom up. So, okay, so post-training deployment, is less effective than growing it up to the thing, So this was interesting because in some sense, basically, there is in this fitness landscape, there are so many minimas to get trapped in. If you are small, it's a simpler landscape and you actually do better. Okay, you can think of it that way. So the results again say starting small, growing naturally may be preferable to simply starting large. Okay. So I'll end here. I think I have finished a little bit, 4 minutes more than I should have, but I'm done now, Sujit. Yeah.
Thank you for the very nice talk. Already there are questions. So can you see Q&A
in the chat box? Yeah.
Q&A box.
Q&A box is different. Sorry. I looked at the chat box. Yeah, sorry, I got this.
Already there are two questions. Can you see that?
Yeah. Okay. If we don't know which nodes are activated after some input, then isn't it possibly deleting a node? Deleting a node may result in the performance. No. So you won't. So if your performance if your performance decreases, then you don't delete the node. I mean, your performance. What did you say? Are you saying that delete a node may result in the performance decreasing, right? So you will, if you delete the node and your performance decreases, you delete it. That's it. I mean, see, there's so much happening in the box. You don't know what is working, in what way. So all you know is that you had nodes, you added it, performance got better, you kept it. You cut one node, if performance didn't get better or stayed the same, you let it go. It could happen that the next time you'll have to add a few extra or do something, it will find an equilibrium, but it finds it very fast and it converges to very small thing. Yeah. So clearly, it is not useful if its performance doesn't get better. So I think, I don't know if I got your question correctly or not. Let me try the second one, and then maybe I'll get back to you. I'll read it again. No, okay, let me try it. If you don't know which nodes are active after some input, then isn't it possible that a result of it? No, so okay. So this, I think I answered. Here, RC training uses single time series to predict the future of the same variable, 2 or more time series. So we did try all of them. We tried ones where the time series had actually, in fact, one that had 3 of them, and we predicted 3 out of it, and some were 1. So we mixed and matched and tried all kinds of tasks. So I have just put it in one class of tasks. But for instance, Manish took the y variable of say the van der Pol and fed it in, and tried to predict the x variable, or took the x variable for the loss and predicted x and y variables, took x and y, fed it in, and did it. So all kinds of things were done. So I'm sure there are more test cases which one should try out. In fact, I was hoping that people might get interested and try out more things, things which are closer to your interest. So indeed, it has to be the scope of it must be checked for many things. But here, this one we check out quite a lot actually, in all kinds of ways. So it wasn't just a single variable. There were multiple. So multivariate input and univariate output was also used for one of them, I think, in the van der Pol or something. Yeah. I saw only. Oh no, there are more. Oh, sorry. I should scroll down. Okay. Someone said they understood the answer. Okay. Does performance-driven network growth provide better generalization guarantees compared to? Okay. So the pruning method is something which for the reservoir computing we didn't do very systematically. But for the feed-forward case, Anil did very systematically, and it was more stable. It was much smaller, and it really worked much better. So there, in fact, we first thought. There was this feeling, you prune and you come to some level, and you grow and you come to a level. Maybe that will be the same sort of size, when we first thought of it. But that was not true. When we pruned, it sort of saturated at a much bigger network, whereas when you grew it, it sort of found a smaller thing. So there was a big gap between that. So, and here the cluster of sizes was very tight for the addition and deletion. For just addition, there was a spread, but here it was converged to a very, it was also very stable. Yeah. and it seemed as if maybe it would lead to, at least in the cases that were tested, it was better than the traditional pruning methods. Yeah. So I will say that this was tested more systematically for feed forward, but not that much for a reservoir. I don't quite know how to do the reservoir so systematically because it will become more like the N1, which we know is worse than the two things which I had. So it will most likely be worse. But but in all fairness, I should say that it was tested more for feed forward. Yeah. How would we adapt this method to a network type where edges are conditional? A task like Boolean network. Yeah. Okay. Right. Yeah. So quick answer. We haven't done it. It sounds like something which should be tried out. It could be of interest. As I said, this is just fresh off the mill in some ways. But indeed, I think we could have variants of the same idea, but could yield dividends here too. We have not tried this. Huh? Okay, so Hitesh, if you would like to go for it, yeah, and try it out. Yeah. So what happens if added and deleted include noise? Uh, so include noise. Oh, you mean to say? Well, it's a probabilistic event anyway. So in that sense, it is there is some inherent chance in every event of addition, and what it attaches to, whether it's input node, output node, what its label is. So all of that is there anyway. So I'm not sure what an explicit noise would do. Um, I mean, you can just there is a margin of like, for instance, the number of links varies between 1 to 5, with equal probability. So there is, in that sense, there is a stochastic element anyway in it. So it doesn't matter too much as long as the basic growth strategy is respected. So even if you added a little more uncertainty in terms of how many are added, or in the error bars, it is probably not expected to make too much of a difference, I would think, because there's some element of chance anyway in it. So there is a spread, like you saw in all the data. There was a spread, because depending on each run would end up somewhere which is slightly different. So there is some spread there, but it's a pretty tight situation. So it's not like a huge spread, like Erdős, Rényi, or uninformed growth, huge spread. So there it will really make a difference, what you did. But for this one, it stays guided fairly close to the course, even in spite of the small random events, which of course happen from time to time. Yeah.
Thank you. Professor Ambika, do you have a question?
Yeah, just one clarification. Sudesh, very nice talk. I just want to ask one thing. Can you comment on the structure or topology of the evolved network? Because the numbers are so small, like 5 or 20. So
right.
It's difficult to fix it with a topology. Also, when you compare it with a random ER network, what's the size of the ER network you are taking? The same as the evolved network, or they are different?
Yeah. So to have an unbiased, fair comparison, everything, when I said something is better than something is small, it's always, everything else is exactly the same. So if I say ER network, it's exactly, so I'm giving the task to a static network of that exact size as the endpoint of the evolved network. So otherwise it's not fair. So so suppose I say 75, then 75 is my ER network, which is the reservoir and is doing its job or not. And sometimes, with 75, ER network doesn't even get to the to the accuracy which it's needed. So it just fails. So because it's not big enough.
Still you keep that size, no?
I keep the exact size, because then it's like literally fair comparison. So all the other things are kept exactly the same. So same with those, all the different uninformed growth, with addition, without addition, deletion, all those things, everything else is same except the strategy. Yeah. And the other question is actually good, because I mean, it is true. Which is why you will notice that I have given you no degree distribution or any such thing, because you're totally right. I don't think it makes a difference. Even clustering coefficient, it's only because the referee was like, oh, clustering coefficient, that we had to do it. But as I said, I gave it a little qualifier myself, because I don't think it's that meaningful a quantity. And even if you see the results, it's not as stark. However, the fraction of readout nodes doesn't matter. Even if it's a if it's a small network, you can see that most of them have gone there. That is very the numbers are so well separated that even in small things it shows up enough. But obviously the really small, the one where it took 5, what can you say? It's for us, the surprise was in 5 you could do the job. That was the real surprise. I mean, because everyone was throwing hundreds and at them, so I was saying, like, really, you don't need it. I mean, that was, I think, the point of that one. But the harder task, there was big enough to have some statistics, but I really don't think the difference is there. I mean, we did look at it honestly, even there, thinking, is it small world, scale free, something. That was not unifying. It wasn't a unifying. So, which is why, if it is not a clean inference, we didn't want to put it. I'm sure it'll be all kinds of things. The other things were very clean across tasks, across everything. So that was the 3 things I said were clean. This one was not. So I don't think it's even probably a feature. There's my gut feeling.
Mostly random like, but we can't say more than.
Mostly random like, They're mostly random like only, but it is sort of got sparser. So it's got thinned out. It is less clustered. That also it is. It is thinned out, less clustered, and somehow its weights have shifted to readouts more than. So these are the 3 things which hold. Yeah.
Good. Thank you.
Okay. Thanks.
Professor Lakshman?
Yeah, I have some basic question. Sudarshan, it was a very beautiful talk. I really enjoyed it. Can you give me some idea of the nature of nodes that you have pursued in your studies? Nodes of the reservoir. Are you using maps, continuous systems?
No, so these were just just a random network where we put random values which went with that equation which I had given with 1 minus alpha RT, and so just that took a vector. So it was not like so it was not like in dynamical systems we start with I have a reservoir of logistic maps. So that was not what we were going for. It was just in the more in the engineering sense of a reservoir. So actually what you said is interesting, because suppose we put this on a reservoir with a certain kind of dynamical system, whether or for instance, I've been thinking, I haven't done it, is that suppose we put say logistic maps, and then I put a spread of parameters, and does it select out a parameter? I have not done it, and this is not what Manish also did, but it's a question actually to put different dynamical systems in the reservoir and seeing if the selected reservoir has a certain type of dynamics. I feel there's a lot of scope in there. I haven't done it, but I feel it's a very good question actually. As I said, more open questions than answers so far. Just started out a bit.
Thank you. Very nice.
Thank you, Professor Lakshman. So thank you, Sudarshan, once again for this wonderful talk. We are very grateful to you. And we are delighted to announce that our next webinar will feature Professor K.R. Srinivasan from NYU, New York University, Tandon School of Engineering. He will be speaking on March 30th at the same time as today's session. Mark your calendars. See you next month. Thank you all.
Thank you, Sujit,
Bye-bye.
for having us.
Bye.
Bye. Bye.